that an exponential function is going to be our a to the power of x. And we also know that our power function is going to be x to the power of a. And actually, I'll use a for both because it doesn't really matter, right? And it's even better, to be honest, to have that criteria on the same. So actually, let's start doing it. So let's construct a L'Hopital's rule. So we take the limit as x approach infinity, and we have our fx, which is our ax, divided by our gx, which is our xa. So we have this. So obviously, both of them is going to be infinity if we do anything. So right now, what we have to do, we want to take the derivative of this. So we have the limit x prime and I'll f prime x, g prime x, okay? And then I'll do this one. So how do you do this? So remember the derivative of a to the power of x is basically natural log a, and then you have a to the power of x. Okay, so ax times natural log a. And the derivative of g prime x, right, any power function is basically a times x a minus 1. So that's what we get. Obviously, it's still going to be infinity. And so let's try again. So limit x to infinity, and then we have f prime double prime x, and then g double prime x. So we have this time ax times natural log a, but squared, because we do it twice, okay? And in case you're wondering why we do it square, well, basically this is a constant. So if we differentiate it, we just differentiate this thing, right? So differentiate this thing, we'll get another natural log a, and ax stays the same, right? So that's why we have natural log a squared. And then divided by, this time is a times a minus 1 times x a minus 2. In your mind, you'll still get like an infinity over infinity, right? Because this is x, you stay here. But before moving on, let's kind of think about this in terms of numerical. Let's try a. If a is equals to 3, especially this far. If a is equals to 3, then we know that basically we're doing x cubed, right? So what happens when we differentiate it? Well, first of all, we have 3 times x squared. And then we're going to have, again, 6 times x. And you differentiate it, it's going to be 6 times x to the power of 0. Okay, yeah. And mind you, because we don't know what a is. But again, what this means is, because this is going to be infinity and this is going to be infinity, unless we're differentiating until we reach something like a 3 minus 3, right, then the power of x is going to become 0, right? 0, x to the power of 0 is going to be 1. So there is a final point, there is a final destination to when we do these type of differentiation. And let's say our a is 4. And you guys are going to see the pattern here. A is 4, x to the power of 4. 4 times 3, okay, 4 times x to the power, so we have 4, and then we 4x3, and then we have 3 times 4, 12x squared here, and then you have 24x, okay, and then finally you have 24 times x to the power of 0. And why do we have x to the power of 0? Is because as we keep on doing differentiating, right, we have 4, we've reached to a point where it's going to be 4 minus 4, therefore we're going to have x to the power of 0, which means it's 1. So here is what we can understand. Okay, so if we have a power function like this, xn, and if we differentiate n times, then at the end, we will get actually n factorial. So why do you think is n factorial? So if you look at here, what do we have when x is power to 0? We have 6. 6 is basically 3 factorial, because 3 times 2 times 1, okay? And 24 is 4 factorial, right? 4 times 3 times 2 times 1, we get 24. Okay, so we have n factorial. So back on this concept, well, this is really important concept number 1. Now we know what happens with power function. And so if we bring this up here, what we're going to get, and we don't know how many times we're going to have to differentiate, but we know that if we differentiate a amount of times, of times, a amount of times, we're going to get something like this. Limit as x approach infinity, we're going to get in below a factorial. Numerator is actually going to be ax natural log a to the power of a. So a factorial actually is a constant, right? Look at these are constants. Constants. So now we know that, oh, this is a constant. And because above there is still an x here, so we know that, okay, so this is going to be infinity. And so the answer to this question, okay, to prove, and we just proved it. So in that case, we know that limit x approaches to infinity, right? Ax is equals to ax over xa is going to equals to infinity. Then because this, we've just proved that our exponential function ax, approaches infinity more quickly than our power function, x to the power of a. And so I hope this makes sense to you. And it is super, super, super interesting. So yeah, thank you.